Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. Today is our lecture number 4, which will be relatively a short lecture on orthosis, where it is about the design and analysis part. So we will try to explain how it works, and from there you will get your first assignment on this section or chapters on orthosis design. So let's move. So we have covered the Wilmington robotic exoskeleton or REX, and this is just to do the review that we have covered. It is a passively gravity balanced orthosis that was developed at the Nemos Alfred I. DuPont Hospital in Delaware. Yeah? So it is designed for people suffering from neuromuscular weakness, assisting them in elevating the upper limbs and improving range of motion, typically for patients with arthrogryposis. So we have covered these where the upper limbs are weak and typically happen to children with arthrogryposis. Okay, so and we have covered all these features of baby with arthrogryposis, and then particularly the upper limbs. We have got the bent or stiff wrist, shoulders turn in, and then the arms are stiff at elbows and particularly weak, and hands and fingers are often very weak. So these are of the upper limbs, and there's a picture of a wonderful boy here which shows the kind of symptoms of having the kind of stiff elbows and weak upper limbs. So we have covered the REX in general. So where it is a lightweight exoskeleton arranged parallel to the arm and fixed to the wheelchair. Then also a second design where it is fixed to the back brace for stability. So basically there are two segments. First, the upper arm link in the shape of parallelogram, and then a forearm limb, just a single rod. Okay, and then there is this linear elastic bands as a linkage between two segments or 2 points, providing a balanced movement against and a safe movement against the effect of gravity. So it's a gravity compensation system. The two sets of rubber bands are arranged to oppose gravity's effect of downward motion due to the weight of the arm and also the weight of the structure itself, providing enough lift to eliminate effects of gravity, but not so much that it overpowers the limited muscular strength of the wearer. So this is schematics of the system, and you can see how it is being implemented in the real actual physical structure. So let's look at the modeling and analysis. I'm looking at the upper arm. Okay, so these are the parallelogram OA, BC is a representative of a basic REX structure. In this structure, the link OA and link CB are free to rotate about the pivot points of O. There's a pin joint here, O and C. Okay, and the parallel structure OA and CB are parallel, connected with a spring of stiffness K. So there is a spring that connects between link O, point O, and point B. Okay, so the angle theta represents the range of motion of the parallelogram structure. So this is theta can move up and down, and that gives us how far we can go up or how far we can go down. Usually, typically, we'll take the neutral position at theta equals to 0 degrees. So this is the neutral position. And this parallelogram shows us what happened when we move the link from horizontal to a certain angle theta. And you can see that if they move up, the spring is somewhat become shorter from the neutral position, and if we move down, the springs become longer, and that extra extension of the spring provide the mechanism by which you can compensate for the movement of the arm. So the arm. So what happens? So in racks, this is unloaded unloaded cases. So you can easily put a load here, load at point A, to take the load of the elbow or the hand, or you can put the load somewhere W/2 at L. But it would be easier for us to put at A. So that's the modeling of the upper part or upper arm of the racks structure. So one particular characteristic of elastic band, if they use rubber band, is that it does not have a compression stiffness. So it is not possible for the structure to have a compression stiffness. This would mean that if we want to have positive support throughout the range of motion, then we must ensure that the spring extension has to be positive within the whole range of motion. One approach to achieve this is to set the system to have enough support for positive vertical force when lifting is done. So you need to do the analysis for the whole range of motion. Maybe you are interested with, say, -60 up to +60, and you need to have enough support for the children to lift their hands. So let us assume that we want to achieve a motion of -60 degree, i.e. that is downward from neutral position. Neutral is horizontal, to +60 degree, which is upward from the neutral position. And the shortest extension of the spring occurs at the position of OB. You refer to the previous slide. And the longest extension of the spring occurs at position OB dash. Okay. And then the fourth observation is that the force from the extension of the spring will create an uprighting moment about point O. And this will compensate the moment due to the weight of the hand and the structures about O. So it is the spring that will compensate the moment of the weight. And the spring, when you extend them, it creates a tension, and from there you can use it for extension or providing the force needed to compensate for the weight of the machines or weight of the hand. So the angle between OCB will dictate the length of the diagonal using the triangle equation. So maybe I need to draw back the system here. So we have a point O, and this is this is O, A, B, C, and this is fixed point, and there is a spring here of stiffness K. So the angle between OCB will dictate the length of the diagonal. So length of diagonal is OB, so OB, and then OB square equals to D square plus L square. I need to check where D square L square minus OB square equals to this is D and this is L. Okay, so this is OB square. So this one is OB square equals to L square plus D square here. And then 2dl cos theta is the initial length. So the force from the elongation of the elastic band can be calculated as F equals to, so when you are deformed, and it's deformed, let's use a different color. So when it's deformed, so A will, because of the rotating, A will go here, A dash, and then it rotates. So B dash is here. So that's your new length. Okay, so d square plus L square minus 2dl cos theta. So the force from the elongation of the elastic band can be calculated as F equals to stiffness times delta x, so x minus x. So where x equals to OB and x naught is the free length of the elastic band. So when you receive the spring, it is unstretched, yeah. So but when you put a force there, so that is x minus x naught. This is x naught, and this is x. Yeah, so that's how we get to this equation, and where x equals to OB, the inertial length, and x naught is the free length of the elastic band. So so the force due to the extended spring acting on point B will create a moment about C. Yeah, and by taking the angle between the spring and the arm CB as alpha, we can calculate the moment about C. Yeah, so going back, so we have that this is O, A, B, C. So when this thing starts to deform, so the spring is extended. Yeah, so that spring produces a force, and we can resolve the force to the vertical and the horizontal. And the vertical force is the F sine alpha. Okay, so that force is F sine alpha. Okay, and that's the angle between the spring and the arm CB. So that's alpha. Okay, so F sine alpha times the arm L. So that's L. Okay, and knowing that from the triangle equation, d over sine alpha equals to x over sine theta, we got x over d square plus L square minus 2dl cos theta over sine theta, the third equation. And we'll get the moment about C as FC MC equals to F L, this is L, d sine theta over d square plus L square minus 2dl cos theta. And that moment C is called the assistant moment. That will help to counter the moment due to the weight of the limb, and also the weight of the orthosis, and also the weight of the external load. So for example, if you put a weight here, let's say you put a weight at point A, yeah? So suppose you put a weight here. That weight creates a moment about C or moment about O. So that moment that you want to counter is this counter moment is MC, and this is the one that will provide the assistance to the person that is wearing the exoskeleton. So moment due to weight is WL if you talk about C. So moment due to weight, I think that's straightforward. WL. You can just put the moment below, that's no problem. Shifting the moment without any horizontal component will make it almost, there's no change. Okay, so it's a way of simple structure that allows us to understand how exoskeleton work. So remember that we cannot have compression for rubber band. So we need to make sure that the spring has a compression if we were to move up, or the spring provide enough compensation when it is plus minus 60. So this is, let's say this is minus 60 degrees, and your design is going to move up another plus 60. So this is the horizontal position. So this is the neutral position. Okay, so again, if we were to design, show it here. So this is neutral, and this is, and that is. So this is minus 60, that is positive 60, and this is our neutral. So the moment C can be called the assisting moment or the counter moment. I can also call it the counter moment. Okay, and these are the one that countering the weight of the limb, and also the weight of the orthosis, and also the weight of the external load. Okay, so now you are ready to carry out your assignment. So this is your first assignment. Yeah. So you have to design a simple rack orthosis, work in pairs. So find a partner. If you cannot find a partner, you have to work alone. Okay. So measure the hand of your partner. One of you will have the hand that is used. So you take the photo and do the measurement. Estimate or weigh the hand. If you have in your home a device to measure your hand, do it. If not, you can do some assessment using anthropometric table. Yeah. So assuming that the hand is paratic, design a Rex orthosis for home-based rehabilitation and also for improvement of activities of daily living. Okay. So develop the equation of motion, as I told you, and prove by calculation, either Excel or otherwise, or you can use SolidWorks model, that the hand is aided by the system throughout the range of motion of interest. Okay. So what I want you, try 3 different stiffnesses of elastic band. So I want you to give me the equation of motion. I want you to give me the equation of motion. And also you have to prove by calculation, yeah, by the Excel or SolidWorks model, depend how. So I want you to plot, give me the plot of countering moment provided by your system as a function of theta. So this is 0, this is minus 60, or I want you to move from minus 60 to positive 60. So I give me your countering moment. I'm not sure how it looks like. It may looks like this. I'm not sure. Yeah. So this is for stiffness 1, K1. You might want to try 3 different stiffness, K2, and then you might have K3. Yeah. So that is what I want from your work on analysis. Okay, and then you submit before 17th of June 2021. Yeah. Which is basically about 3 weeks from now. Okay, so remember, you have 2 systems. I have shown you the first system. Let me show you. So remember, you have got the first system. So this is your first system with your K. And please remember, you have another hand. Yeah. So I think this part is basically easy for you. I think this part is not that difficult. Yeah. So you can do that analysis. And how do you provide the weight? So the assumptions of the weight. So I would assume that my weight of the hand is here. Okay, lower hand. And then my weight of my upper arm is here. Okay. And then I would assume that the weight of the limb is here, the weight of the structure. So let's say W, whatever, WI, and then all the weight of the structure is in the middle. Yeah. So this is WJ, etc. So I think you can do the summation of the calculation, and at the end of the day, provide me with the graph of the countering moment from minus 60 degrees to plus 60 degrees. So work in pairs. Try to get the measurement of your friend, your arm. You need to know the length between the shoulder, the elbow, and also the pivot of the hand. You need to draw the support, and yeah, so that's you need to draw it. Yes, you need to draw the system. So use SolidWorks to draw it. So use SolidWorks to draw. Use SolidWorks to draw. Your Rex Orthosis. Okay, so submit before 17th of June. Not that difficult, I hope. So all in, your report should not be more than 4 pages. Report 5 pages max. Don't do more. That's including your drawing, including your CAD. Okay, so I would like to stop there for the design and analysis. I hope you take the extra time to do discussion among yourself and get back to me if you have any problems or any questions. Okay, that's the end of our orthosis for the upper limb. Before next lecture, we will move to the orthosis of the lower limb. Okay, so the assumptions are your design the rack that it will compensate 90% of the weight of the upper arm and 80% of the lower arm, your hand. This maximum compensation should be at the neutral position where the end and the hand are fully extended. From there, individual range of motion can be calculated. For this design exercise, the range of motion is limited to plus minus 60 degree from the neutral position. So neutral position is when your hand is extended. So neutral position is your hand is so that's neutral. Neutral position. Yeah. Okay. So complete SolidWorks CAD drawing of the racks with dimensions 20 marks. Design calculation and one example 20 marks. Graph of supportive movement versus angle. Video of a moving SolidWorks 20 marks. Design of the results. Discussion of the result 20 marks. Format and references 10 marks. Report should not be more, sorry, it should not be more than 6 pages including references and your CAD. Yeah, plus CAD. Cannot be more than 6. I'm okay with 5 pages too. Don't be too much. So form a pair, form a team of 2. If you cannot find a member, then you work on your own and ask around. Okay. All right. That is the lecture for number 4. I hope you have benefited from this lecture, and we'll see you in the next lecture on lower limb orthosis. Thank you very much. Assalamu alaikum.